Warning: the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. We now step into solving exponential and logarithmic equations, specifically in this video, solving exponential equations. And notice that the title of this says Solving Exponential Equations Using Logarithms. Well, there are other ways to solve exponential equations, but the most traditional way is by use of logarithms. And in fact, that's pretty much how you're always going to solve them from pre-calculus and forward, really college algebra and forward. So we might as well just focus on that. This all relies upon one simple idea, the definition of a logarithm, which is that log base b of x is equal to y if and only if b to the y is equal to x. Now, when you're dealing with logarithms, you do have to worry about domain issues, and so we'll approach those as we kind of go through and solve. But it is important to remember this notation. Now, notice that this first equation we're being asked to solve is an exponential equation. It's an equation that involves unknowns that are within exponents. So that's why it's called an exponential equation. And the way I'm going to solve something like this is really by applying the logarithm to both sides. So I definitely want to showcase that before we start. Suppose that you have some exponential equation like this. It doesn't have to be y in the exponent and x on the right hand side. It could be whatever pictures you want. It doesn't actually matter. The most important thing is that we are asked to solve for whatever's in this exponent. How to do that is to take the logarithm of both sides. And I will showcase that here. It's kind of, this example is not the best, to be very honest with you, because the base of the logarithm that I'm taking is the same as the base of the exponential. And that won't always be the case. In fact, it rarely is. But we can use properties of logarithms in this specific case and say, oh, that means that y is equal to log base b of x. It's that action that I just took of taking the logarithm of both sides that we are going to enact for all of our solutions to exponential equations. So let's dive into this with this example. We're asked to solve this 3 times e to the 4x plus 1 minus 4 is equal to 20. It could be as ugly or as nice as we want it, but I kept it kind of nice here. You want to start isolating the variables. So add 4 to both sides, divide both sides by 3. And when I do this for college algebra students, I don't bother with the slow process. I just know I'll have 24 divided by 3, which is 8. And we get to that point. Now, before we continue, do a logic check. An exponential function, b to a power, is always positive. So this exponential function we have right here should be equal to a positive number. It is. So I'm free to continue forward. If that was a negative 8 on the right hand side, I would immediately say no solution. That's a good logic check without you having to continue forward if you don't need to. But let's continue forward because we need to. I'll take the log of both sides. In this case, I'm going to do the natural logarithm because this base on this exponential function is base e. Doing that, I'll have the natural log, whoops, except I need to use the right pen. The natural log of e raised to the 4x plus 1 is equal to the natural log of 8. Notice I applied the natural log to both sides, just like you would add 4 to both sides, or divide both sides by 3, or square both sides, or whatever. Whatever you do to one side of the equation, you must do to the other side of the equation. And of course, the natural log has a base of e on it, and so therefore the natural log base e of e to the 4x plus 1 is 4x plus 1. So I'm going to write this as 4x plus 1. This is just using a property of logarithms. I will then subtract 1 from both sides. Basically, just solve for x. Subtract 1, divide by 4. Now, probably the most common mistake at this point is not following the order of operations, but I subtracted 1 from both sides and then divided both sides by 4. This is my final answer. You're more than welcome to check, but you actually don't have to as long as you did the logic check before, where you zoomed in on this and you said, exponential function equals positive number. That's correct. Then there's no real need to check your answer in the very end for these styles of equations. So let's try that solution method again, but in a bigger framework. The whole point of exponentials and logarithms, well, not the whole point, but really where they're most important is in applications. And that, if you're one of my students, is where you're going to see them the most. Is I'm going to just hit you with application upon application upon application. So you have to get used to word problems, as they used to be called. So this is one that I just did some, quick research on. So on January 22nd, 2020, there were 313 confirmed cases of COVID-19 worldwide. As of September 27th, when I wrote that problem, 2020, there were 32,929,407 confirmed cases. Build an exponential model representing this situation and start, I think I did this before, state the daily growth rate. Now, I copied this problem from a previous lecture, but there's more to it now. So state the daily growth rate, and that's all I really need. Don't worry about the daily growth factor. We did that in a previous problem, and the monthly growth rate. Don't worry about that. But what is important is build a model and use it to predict when the equivalent of the population of the United States will all have COVID-19. In other words, build your model and then use your model to predict when the population of confirmed cases across the planet equals the current population of the United States. Now, as I said, we did this in a previous video, but it's always nice to kind of do things a couple times just to see it. So at time 0, there were 313 confirmed cases. And then as of September 27th, there were 32,929,407. We just need to know how many days there were between January 22nd and September 27th. I just quickly looked that up. That's 250. And so we have 2 points here, 0, 313, and then 250, 32,929,407. Again, just to review how you would build an exponential model, all exponential models, at least in the real world, kind of look like this. And so we have a couple points. That's all you really need for an exponential model. We know that at time 0, so I'll just plug in 0 for time, our output is 313, which tells us, remember b to the 0th is 1, that p naught is 313. So therefore our population at any given moment is modeled by 313 times some unknown base to the t power. To find that unknown base, we just plug in the second point. When t is 250, our output is that 32,929,407. Solving this for b, and I'm not going to go through the painstaking conversation of how to solve this because I did that in the previous video. I'll just say that b is equal to 32,929,407 divided by 313 raised to the 1/250th power. And I will actually use Desmos to approximate this because, well, I might want to use that base exactly later on. And you can see it right here that value of b is roughly equal to 1.047. I'm going to actually round it on my paper to 1.047, but to be very honest with you, I'm going to use that exact value, or close enough to exact, for all my computations. And so there you see, I've just written down that B is roughly that. And so our population model, again, for those who have confirmed cases of COVID-19, is 313 times 1.047, roughly, I should say, not equals, but roughly, to the t power. And now what I'm going to do is go ahead and finish asking or answering this question. We've built a model. Now we want to use this model to predict when the equivalent of the population of the United States will all have COVID. So that means we need to know what the current population of the United States is. And I really like using the internet during lectures and stuff like that, because it really allows you to feel like you're using real world data. There is a problem here that this is actually an approximation. You can see that little ticker is moving. That does not mean that all of a sudden this is keeping track of when a baby gets born. So what I'm going to do is I'll just copy this to the 657 part. So 330,381,657. So really we're being asked to solve this equation. 330,381,657 is equal to our population model. By the way, in the time it took me to write that, 4 babies were born. And something else here that I think is really helpful, because I'm not going to be using this approximated version of our growth factor, I'm just going to put B in here because I saved that B in Desmos. So I'm just going to leave it like that. It's always a good idea if you have an exact value just to use a letter or a variable to represent that. And let's solve for our time value. How long does it take? How many days since January 22nd until the equivalent of the United States population has been confirmed with COVID? So divide both sides by 313 and we will get the following. And then you just take the logarithm of both sides. And it actually doesn't matter what base you do. Well, actually it does kind of matter what base you use, because the reality is most computers and calculators do not have anything other than log base 10 or log base e, natural log. So I'll take the log base e of both sides. So the natural log of both sides, just because I want to. It'll give you the same answer, by the way, if you do the log base 10. So it doesn't really matter, but I just want to do the natural log because I want to do the natural log. No other reason. And notice when I take the natural log of the right hand side, I can take that exponent and move it out front, right? That's exactly why you take a logarithm, to unlock an exponent. And to isolate that value of time, I'll divide both sides by the natural log of b. And so now we can go over to Desmos, which has our value of b already saved, and just type this in. And notice here that in Desmos, it's really nice because one, you can really kind of see everything clearly versus just a graphing calculator. And two, you just type in ln. Watch your parentheses. And that's all you have to really watch out for. I'm using the value b that I stored up above, and we're going to go ahead and round the number of days to the nearest day. So 300 days. So roughly 300 days after January 22nd. So that's not too long. Roughly about 2 months less than a year. So maybe around Thanksgiving. Yeah. November 27th, somewhere around there. Probably around Thanksgiving, where, according to this model, there'll be the equivalent of the United States population that have been confirmed with COVID. So you can expect that style of problem when you're dealing with exponential models. They are pretty fast to solve. They're not too terrible. And I think it's very doable. Let's see what else we have. When it comes to solving exponential equations, you definitely are going to run into stuff like this. It's not always going to be a single exponential function. In this case, you have 2 exponential functions mixed in here. And you should have seen this already in a college algebra course, not this specific equation, but this style of equation. It's called quadratic in form. And the reason why it's called quadratic in form is because if you move everything to one side, so we have e to the 2x minus e to the x minus 6 is equal to 0, you can make a simple substitution. Notice the power on this first term is double the power on the middle term. And because of that, it screams and begs for a substitution of u is equal to e to the x. We call it a u substitution in mathematics. And if you square that u, you will have e to the x being squared, but we know that powers to powers multiply, so that's e to the 2x. So wherever I see an e to the 2x, specifically right there, I'm going to replace it with u squared. Wherever I see an e to the x, specifically right there, I am going to replace it with a u. So this becomes a u squared minus u minus 6 is equal to 0. You do not have to do u substitution here. You could totally factor this without doing a substitution. However, I find that it is helpful for students who are still kind of at the college algebra phase to kind of do this way. Factoring, this will be u minus 3, u plus 2 is equal to 0. And then that implies, since we have a product of two factors becoming 0, either the first is 0, which means u is 3, or the second is 0, which means u is a negative 2. You didn't start in the world of u's, so you have to trade back out. Do a resubstitution. U is e to the x. So this implies e to the x is 3, or e to the x is a negative 2. Logic check. Exponential functions are always positive. Well, that throws out any need to look at that. Notice I completely avoided working with one full equation just because exponential functions are positive, not negative. So I could throw that part out. Now I'm just going to go ahead and finish out the problem by taking the natural log of both sides of that bad boy right there. If the natural log of e to the x is equal to the natural log of 3, of course, natural log base e of e to the x is just x. So x is equal to the natural log of 3. I'm boxing that up because I really don't want to check it because I know it's going to work. I already threw out the one that won't work. All right, I think that pretty much covers solving a review of solving exponential equations. We did a quadratic and form exponential equation. We did an exponential model, and then we did a basic exponential equation at the beginning. So that covers all the basics for college algebra.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.